Okay, can you see my screen?
Yes.
Yes. Yeah. Yes.
Okay. Okay, so thank you. I'm going to break this presentation down as follows. I'm going to talk a little bit about the motivations and some of the challenges for space app and communications and how that is tied to additive manufacturing. Then I'm going to talk about the filters I have, in particular 3 of them. And then finally, I will conclude this presentation. Okay, I want to start by talking about the investment towards space communications and why it is important, because in a way, we're all related to it. And one of the tendencies that has gained more popularity over the last years is global connectivity. And we're pretty well wired with optical fiber, with infrastructures that provide internet easily. But there are regions, even in more developed countries, where there's still not even coverage or nothing whatsoever. Building infrastructure is expensive and might not look good to the naked eye in some areas. And one trend nowadays is the investment towards big constellations of LEO satellites. Some companies are planning to put in orbit around 1,600 satellites, but these bring some challenges. Time and being able to produce components for volume production, and also the mass, which increases the price of the satellite. So you have to find ways to make these more cost effective. Okay, among many different fields under study, and currently one of them that is becoming more popular is the use of additive manufacturing techniques. The advantages that provides are in fact very interesting and can solve some of the issues I was talking about, but there are still some challenges. We have to provide components with multiple characteristics by exploiting the flexibility that additive manufacturing can offer, and find ways to optimize the space. And for microwave components, specifically filters, find ways to obtain high quality factors. Okay, if you look at some of the work that's been done, actually, we know that, for example, techniques like SLM is bridging the gap between prototyping and the actual implementation within the industry, even in the field of microwave components. And in my case, the focus is on filters. And when choosing one technology to design a filter for the job, and we look at losses, power handling, size, and volume. And you can actually find a variety of these types of filters within the communication system of a satellite payload. And since losses are critical at the early stages of the communication system, waveguide filters are still a key technology for onboard RF satellite systems. And in particular, throughout this presentation, I'm going to talk about cone line and cavity filters. The goal here was to find new designs related to these 2 types of technologies, but be more compatible with the additive manufacturing and take advantage of what some additive manufacturing techniques can offer. So in the next 10 minutes or so, I'll show 3 types of filters that we have done using 3 3D printing techniques. So the first one, it's a cone line filter. So in this case, we presented an alternative to cone line filters. And the idea behind was to provide a different structure that could provide the same response, but with the advantage of saving volume, and also give a new configuration that could be interesting depending on the requirements of the telecommunication system. Basically, it works by having a resonator inside a conical housing, which could also work as another resonator if we stack another cavity on top of it. And these type of structures are well suited for additive manufacturing, a motivation behind this work. Okay, some of the results are shown here when comparing with more classical cone line resonators. For instance, a comparison between quality factors and volume was carried out. And looking at some of the data we obtained, we actually save about 30% of the volume while maintaining the same quality factor. And it also presents a wider spurious-free range. And this is actually a consequence of the insertion of the resonator inside the conical housing placed on top of it. Each resonator works as a reentrant post where a larger capacity loading around the top of the cone is generated and is larger than the classical cone filter, and that's why the next resonance is further away. So in this case, the reentrant post is an advantage to design filters in different arrangements. So we can design filters vertically, horizontally, or as a combination of vertically and horizontally structures. So here I'm showing a vertical filter, 3x1, 3 cavities on top of each other, and also a 4-pole filter, 2 horizontally and 2 placed vertically. On the right of each filter, we can see the scattering parameters. There is also the possibility of having transmission series as long as we use a combination of vertical and horizontal structures. This is just the bottom part of the structure meant to be built from here all the way up. The one on the right. There is an electric probe attached to each resonator and facing each other with a small gap in between. That actually helps to control also the position of the transmission series. This way we can create a coupling between the first and last resonator with an opposite sign with respect to the other couplings, resulting in one transmission series in the upper and another one in the lower stop band. Here's an example of, in fact, a 6-pole filter, 3 cavities on top of each other, but also 2 horizontally. This is the first prototype. This was done in collaboration with the University of Pavia, and the additive manufacturing technique employed was the so-called polyjet technology. Here, on the other hand, we fabricated a 4-pole filter using the same technique and the same, let's say, galvanization process that it was used for adding copper around the filter, since this technique produces plastic components. So the next filter is a spherical filter. If we compare the 3 basic types of cavities, rectangular, circular, and spherical, it turns out that it's the spherical, the one that has the highest Q factor. The circular cavity is close, but it has a larger length. And the rectangular one has the lowest Q factor, but it's a lot easier to manufacture with more traditional manufacturing techniques. However, the spherical cavity has gained more popularity because it can be manufactured easily with additive manufacturing techniques. So in this case, the idea was to exploit a higher order mode in order to achieve high quality factors. The spherical modes are classified in TM and TE. The first 2 are TMs, and the third one is a TE mode, which is in fact the one we are interested in. Its electric field takes a sort of circular pattern around its center, and it is in fact similar to the magnetic field of the fundamental mode. What's interesting about the spherical cavity is that it presents a higher quality factor than the rectangular and circular cavity. And in this case, this mode presents a quality factor when considering a luminance of 23,000, which is almost double the first 2 TMs. But in order to resonate at the same frequency, the radius is increased about 1.61, that of the fundamental mode. And this could actually be an interesting advantage, especially considering a cavity operating at higher frequencies. And this could improve tolerances as the radius will actually be higher than the fundamental mode, and provide even a higher quality factor at higher frequencies, which is a real challenge. Okay, we can excite this mode in multiple ways in order to design filters with different types of responses and different positions of the generated transmission serum. Here I'm showing, for example, 3 types of topologies that we can obtain in which we have different positions of the transmission serum. So to manufacture the filter, we went for the technique called SLM, and here's an overview of the process. And as it is common, one of the next steps when it comes to designing a filter, especially using SLM, is designing a filter more compatible with a 3D printer. The changes are made as to improve the tolerances, but also to avoid adding supporting structures. For example, considering a 2-pole filter, one change is the middle aperture for a more ellipsoidal cavity, and ellipsoidal shape, sorry. And you do this to give a self-supporting capability and avoid adding supports, especially inside. And the component was built layer by layer in a vertical direction without inclination and with the spherical cavities at the bottom. For the fabrication, the powder that was used is the aluminum alloy that provides an accuracy of 0.1 millimeter. In the SLM process, different powders can actually provide better or worse manufacturing tolerances, better or worse mechanical properties. So it's a trade depending on what you're looking for. Okay, we started with two prototypes based on the same filter with a fractional bandwidth of 1.3%. And surprisingly, both showed almost identical results with a frequency shift of 45 megahertz and a return loss higher than 30 dBs. If we look at the insertion loss, and we obtain a value of around 0.07 dBs at midband and 0.1 at the edges. As a result, the measured quality factor in this case is 4500, and for both of them, as opposed to the value of 11,000 from the simulation using aluminum. This filter is currently being studied though in order to maximize the quality factor. Still, if you look at some of the work that's been done where filters were fabricated, even when silver plated, it presents a higher quality factor. So the next filter I'm going to talk about is somehow similar, as it was initially based on the same cavity. We try to find ways to reduce the size of the filter, and one way to do that is to work with dual mode resonators. And dual mode resonators are extensively used in modern communication equipment. They can implement very sophisticated and selective filter transfer functions. And in waveguide filters, one option is to increase the size of the cavity, as it allows other modes to be excited within it. But other ways is to work with degenerate modes. And this is quite common and widely used. It is based basically in using tuning elements to couple orthogonal modes and use some extra tuning elements to adjust their frequencies. However, this brings some level of complexity when it comes to the design and manufacturing. And using circular waveguides, you can actually achieve higher quality factors, but the length of the filter is larger than the rectangular cavity filter, for example. You can find in the literature dual mode filters using spherical cavities based on the same configuration that we've seen. And this is a full pole filter and implements two symmetric and not controllable transmission series. And that is possible as long as we have a minimum of two cavities. And this is not a desirable feature for high volume production when we have to work with tuning elements, as they can degrade the Q factor and also cause degradation in the out-of-band rejection response. So in this work, we decided to use ellipsoidal cavities, and ellipsoidal, like this one, has a surface that may be obtained from a sphere by deforming it by means of directional scaling along the X, Y, or Z axis. Here I'm representing the frequency when changing the ratio Rx, Ry. And when this ratio is below 1, the frequency of the mode polarized along the X-axis changes more rapidly from higher to lower frequencies than the frequency of the mode polarized along the Y-axis, which is almost constant. And when this ratio is 1, we have a sphere. So we can design a filter by including input and output with a certain rotation, theta, here and also here, but in the opposite direction. And this implements the transverse topology that is shown here on the right side of the slide with two modes excited, one along the X-axis and another one along the Y-axis. And this realizes two poles and one transmission zero, the position of which can be controlled with the rotation. So the starting point is 45 degrees, and in this case, no transmission zero is implemented. If we lower this rotation, we can see that the transmission zero is placed in the lower stop band, and as we decrease this value, it gets closer to the passband of the filter. And for higher values than 45 degrees, the transmission zero is placed in the upper stop band, and as we increase its value, it gets closer to the pass band. Okay, so in order to prove the feasibility of the proposed filter, we designed and manufactured and tested first a two-pole filter. And here, for example, I'm showing the measurements of a two-pole filter at around 10 gigahertz with a transmission zero in the upper stop band. And this was manufactured using a SLA 3D printer, a technique that is very similar to the polyjet technology. And since this also produces plastic component, we decided to have two parts of the filter and then use a galvanization process in order to add layers of copper on the inner surfaces. And higher order filters are possible, and we can do these by cascading doublets with or without non-resonating nodes. Here, for example, I'm showing us the simulation and the measurements of a four-pole filter without non-resonating nodes. And in this case, we decided to place the transmission zero in the lower stop band. So, okay, and throughout this presentation, I wanted to show you three types of filters that we have designed and fabricated that are more compatible with the 3D printers. So the first one was a comb-line filter. It was intended to be designed in order to reduce the volume while providing also different arrangements. The second one is a spherical filter. We did this in order to obtain high quality factors for filters fabricated in additive manufacturing. And the third one is an ellipsoidal filter that has been designed in an inline configuration, and we can obtain asymmetric transmission zeros, the position of which can be controlled. And no need for tuning elements are needed. And as for future work, we want to investigate more other metallization techniques that could actually improve the results, especially when considering techniques like SLA. And also investigate other mechanical designs that